Yes. So yesterday we got this equation. Okay. Okay. This is the equation. This is a very general basic equation called Schrodinger's equation. So from this equation, put all the conditions, boundary conditions, and evaluate psi. Once you evaluate psi, that will be the solution to this equation will be the psi. That is a wave function. Again, you have to remember that there may be multiple solutions to this equation. So you may get psi 1, psi 2, psi 3, psi 4, or any number. After that, what you have to do, you have to put the conditions. What conditions? Well-behaved wave functions conditions. When you put that conditions, well-behaved wave functions, you will end up with one or two wave functions or more than one or two. But all of them would be defining the same particle, right? All of them would be defining the same particle. In that case, they all would be similar. They all would be similar. But in many cases, it happens that, see here we started with a particle and its energy was E is equal to P square by 2m plus U x of x into t. See, U of xt. That is the potential energy as a function of x and potential energy U as a function of x and t. But okay, potential energy as a function of x and t. But in many cases, potential energy need not depend on time explicitly. Okay, it depends only on position of the particle. Potential energy of a particle doesn't depend on the time explicitly, but it depends only on the position. In that case, the function what we considered, the equation what we considered in the previous slide, this equation where we have the time dependent part, this is time dependent part, and the other is position dependent part. Time dependent part, position dependent part. And I said it may not depend explicitly on the time. The wave function may not depend explicitly on the time. It only depends on the position. In that case, we will have to get rid of this, or we will have to call it as a constant. This one we can make it as a constant, right? Constant. We will have to make it as a constant. So when we make this as a constant, instead of psi, we will get a different wave function. We will get a different wave function. Let's see how it works, because in most of the cases, we will be using that equation, not this equation. So,
sir,
yes.
In what conditions we get time independent, sir?
In many cases, just for the time being, you just take, in most of the situations, we get time independent wave functions.
Okay, sir.
Okay. So here we have this ET. This ET could be taken out and it can be considered as a constant, right? And our wave function will constitute only of I by h cross into px. So that is what we are going to do. So this we call as Schrodinger's equation in steady state form, or Schrodinger's time independent equation. So this is the wave function equation, general wave function equation, which we got from the wave equation. So this wave function will separate it out as, here it has time dependent part and position dependent part. We will write them separately. So here we have the time dependent part and we have the position dependent part. This is the position dependent. Now we'll take this A and this position dependent part together, these two together, and represent as psi. Sorry, I'll call this as phi for the time being. Okay. So these two together have been represented as phi. And this e to the power of minus IE by h cross t, which is a constant, or which doesn't influence the particles. Okay, which doesn't influence the particle actively, is kept separately. So note down this. If it is over, let's move on. Next, we have E psi is equal to E into phi into e to the power of. See, what we have done is we have taken the previous equation and we have multiplied this equation. Wait. This equation. In this equation, IH cross dou by dou t is E, right? Here we have IH cross dou by dou t, E psi is equal to IH cross dou by dou t into psi. Okay, that we have substituted here in the same equation. That you give an equation number to this. Which equation number you want to give? 5, 6 is over, 7 is over. Let's give equation number 8. Equation number. Equation number 8. Okay, now call it equation number 9. Okay, next, substituting equation 9 in 8. Substituting equation 9 in 8. Substituting equation 9 in 8. We'll get this. Clear?
So the left one is psi, sir.
This is actually slanted one. This one is slanted. All throughout, wherever you see psi, it is slanted psi. It is not the original upright psi. This is upright. This one is written as slanted. Slightly. You write the upright psi as like this and slanted psi as like this.
Sir, how will we get that one if we substitute?
You will get it. Simple. Wait, I'll show you. Just a minute. Where is the last equation? You get it. Control C. See here. This is equivalent to E, right? This is E psi. This they have kept as it is. This is U psi. So instead of psi, you substitute this part. This part should come in place of psi. Whole of this. Whole of this should come in place of psi. Then here you differentiate it twice and write. You will get the same thing. Because here e to the power of minus IE by h cross t is a constant. So you will get it out. Differentiate this twice. That's it. That means just replace. Instead of psi, you replace it with this full term. So d phi stays inside and this comes out because it is constant. That's it. Plus u into, again the same thing. Write down this first. This clear? You got it? Did you get this step?
Means we have to differentiate it, na, sir?
Which one?
The ninth one. I mean, the
Wait.
ninth one substituted in eighth one.
Wait. Give me a minute. Give me a minute. Give me a minute. This one you understood, right?
Yes,
This
sir.
one you understood. This one, separation of time dependent and time independent region parts.
Yes, sir.
Yes, sir.
Next, you rewrote this like this, right?
Yes, sir.
Then write down the equation and write down this. Here we have the equation. Write down this. And
Yes, sir.
this you rewrite as, replace this part with E. Replace this part with E and rewrite as E psi is equal to, this is upright original psi. I haven't replaced it with phi. Okay.
Sir, once you show the E psi value in the previous slide, sir.
You check. You should be having, right? Did you take down? See here. Can you see this?
Yes, sir, but here E psi is equal to
Wait.
minus h by I.
Minus I. Multiply and divide by I. What do you get? Multiply and divide by I. What do you get? Minus I h cross by minus 1, right?
Yes,
I
sir.
square is minus 1.
Yes, sir. Yes, sir.
Then what do you get? Minus h cross dou by, sorry, I h cross dou by dou t. Yes?
Yes, sir.
That's it. That is what I have written. Itself it is changed, right? See here. Multiply and divide by I, you will get rid of I in the denominator as well as the negative sign. Clear?
Yes, sir.
Yes. Now what you have to do? You have to, wherever this psi is there, wherever psi is there, you have to replace with this term. Full term you have to replace. Right? Write down that quickly. over, when you replace it with full term, when the psi is replaced with that full term, that is phi into e to the power of minus IE by h cross into t, this is what you get, right? E into phi e to the power of minus IE by h cross t is equal to minus h cross by 2m, h cross square by 2m, e to the power of minus IE by h cross t, dou square psi by dou x square plus u psi e to the power of minus IE by h cross into t. This is what you get. Yes or no? Now divide throughout because this part, see, this is constant throughout, and both sides of the equation this is existing, right? So divide throughout by e to the power of minus IE by h cross into t, so that what you get? You get this loose. What is left over? Left over is this equation. Dou square psi by dou x square plus 2m by h cross square e minus u into psi is equal to 0. That is what you get. Clear? Any doubts here?
Excuse me, sir.
Yes.
So my screen is very blurred due to network issues. So like I can't make out like which is T and which is I. In the first row, could you please tell me? That last, like the
Which
last
one?
equation. Last equation in the first row.
Here, this is I. Can you see this? My writing?
Yes, sir.
This is I, this is T. Okay.
Okay, thank you, sir. Even in the previous ones, the first
Same.
one is I, the last one is T.
Yes.
Okay, sir.
Sir, how it
Yes.
how it became 2m by h cross square, sir?
Simple adjustment. You will have to do E psi, right? What you get from this? E psi. E phi. E phi I will call. E phi. Okay.
Yes, sir.
Minus u phi. Right. I have brought this side. Is it okay?
Yes, sir.
Okay. This is equal to minus h cross square by 2m into dou square phi by dou x. Is this clear till now?
Yes, sir.
Just now rearrange. That's it. You take this. Take a bracket here. Take this here. Okay, and then bring this.
Okay, sir. Okay, sir. Okay, sir.
That's it. But in three
Sir,
dimension. Yes.
you have divided this one, sir. Last one.
Which one?
This last right side one.
Not divided. This one you are talking. Huh?
Right side. Yes, sir.
This one is in 3 dimensions. Here we have taken only x with respect to x. That is 1 dimension. Right? Schrödinger's steady state equation in 3 dimensions would look like this. Dou square psi by dou x square is that means it is only along x axis, or 1 dimension. Right? Take it in 3 dimensions. Dou square psi by dou x square plus dou square psi by dou a square plus dou square psi by dou z square plus 2m by h cross square e minus u. So this is the Schrödinger's time independent equation in 3 dimensions. Write down the last one. Schrödinger's time independent equation in 3 dimensions. Yes. Any doubts? Feel free to ask any doubts, guys. If you don't understand, please let me know. Don't hesitate.
Sir,
Yes.
sir, if you don't mind, E psi is in the previous slide you told that E psi is equal to minus h cross by I into rho psi
Yes.
by rho t, sir.
Yes.
But here you took E psi is equal to I h cross into rho psi by rho t.
Here I showed, no? See, here I showed. I have shown it here. You didn't get here.
Sir, this one I understood, sir. This equation, okay, sir.
E psi
From
is
this-
equal to, I get I h cross. Okay.
Sir, minus h cross by, no, sir.
I am multiply and divide by I.
Oh, 1 second, sir.
You get I here, I square here. What is I square equal to?
Minus 1, sir.
Minus 1. So minus minus gets cancelled.
Okay, sir.
Then what I get? I h cross dou by dou t. What is remain?
Yes, sir. Yes, sir.
Can I write E as E is equal to I h cross?
Sir, now understood, sir. Sir, also when substituting 9 in 8, you have done the differentiation of ninth one, sir.
Wait. Ninth one. No, I don't have to do the differentiation.
Means this one, sir. This left one equation came, no, sir.
Yes,
You
this
cancel
one,
that.
right? You are saying this one. Huh?
Yes, sir. Yes, sir.
This one you don't have to do the differentiation. I substitute instead of psi, I substitute this whole part. Okay.
But there is
This
a rho,
whole
no,
part.
sir.
Huh?
Rho is there, no, sir. Rho by rho t.
Rho na. Hey, there is no rho by rho t, man. Where is rho?
E psi is equal to I h cross into rho psi by rho t, no, sir.
Where rho?
Sir, not rho.
Hey, do man.
Yes.
Do square
that
psi
one.
by. No, there is no t part here at all.
Sir?
No. That is why I haven't, instead of I h cross dou by dou t, I have written it as E. See here, this I have replaced with E here. They are equivalent.
It is function, no, sir. Rho by
They are,
rho
yes,
by dot.
they are equivalent. That is why I have put it here. And here, this doesn't depend on T. So I have put it as E. We can write it. Not an issue.
Sir, means dou by dot t should always it is a function, no, sir. So it have
I
to
understand.
differentiate.
I understand.
Sir, even I
Whenever
have
there
the
is
same doubt.
whenever there is I h cross dou by dou t here in quantum mechanics, that is equivalent to energy operator. Okay, that you will understand in maybe in next slide. Okay, we can write it as E. To simplify the things, I have straight away taken it as E. There is nothing wrong in that.
So
You don't
E
have
is
to
an
differentiate.
operator.
Yes, it is operator. That you will understand later. Okay. So it is equivalent to E. It is equivalent to E from the previous equation I have shown. That's a very good observation. So I have taken it as it is because I didn't want to complicate the things.
Okay, sir. So we have to remember that function also as E.
That function you will have to remember. I will tell in the next slide. That's a good observation.
Okay, sir.
Good, guys. Yeah.
Sir, and
Is
then
it
why
clear
did
now?
we do? Sir, why did we do partial differentiation instead of differentiation?
See here, always you'll have to what do you say?
Is it so that we can eliminate the other dimensions, sir?
No, nothing like that. Here you are talking with only one dimension. That is not an issue. That is not an issue. I'll come back to you. Let me. Okay. Back to it. It's fine. I'll get back to it. But now let's continue with this. Okay. I'll tell you. Okay. The final equation is dou square psi by dou x square plus dou square psi by dou a square plus dou square psi by dou z square plus 2m by h cross square. So this is the final equation, which we call as Schrodinger's time independent equation. Right down. Schrodinger's time independent equation.
Sir, which ones are the last 3D one or 1D one?
3D1, 3D1, 3D1.
Sir, once again, can you repeat that point, sir? This is
Schrodinger's time independent equation. Okay.
This is equation 10, sir.
Sorry?
This is equation 10, sir. Last equation.
You can put an equation number for that. Sorry. 10, right? Just a minute. Hey, who is watching TV, man? Vico Vachradanti. Mute yourself. Okay. If it is over,
So, excuse me, sir. Excuse me, sir.
hey, Palaniswamy, Arun Palaniswamy. Arun Palaniswamy, where is he? Yes.
Sir, in the last equation, is it the regular psi or the slanted psi, sir?
It is actually slanted psi. It is actually slanted psi. But hereafter, we will call that also as wave function and we will move on.
Okay, so then we have to substitute value of the slanted psi and all that.
Yes, it is slanted psi.
Okay, thank you, sir.
Okay, for now. Next is the expectation values. What is this expectation values? See, in the beginning itself, I told what we are discussing here is the probability. Probability of the position of the particle. So particle may be there with this percentage. Particle may be there with that percentage. Particle may be there with 20% chances. Particle may be there 50% chances. Particle may be there 80% chances. So these expectation values are the most probable values. It is called as the most probable values. Write down expectation values. So this expectation values we derive for each quantity. That is, for the location, we extract the expectation values. For the energy, we extract the expectation value. For the momentum, we extract the expectation value. For everything here, we do not have any precise value. Always we go with expectation value. It is the most probable value that is expected for that particle. So write the definition. Expectation value. It is the most expected value of a quantity. Quantity means it may be position, momentum, energy. Okay. Full stop. it also gives the average value over a range of limits. Okay, so now let's say we have a wave function. This is a wave function, a typical wave function. Psi is equal to AX. Right. This wave function is extracted from wave. How did we arrive at this wave function?
Sir, is this one a formula, sir? Psi equal to AX.
Yes. Psi is equal to AX is not a formula. We say it is a wave function.
But
Okay.
psi is equal to another thing is there, no, sir?
Which
A
one?
into e power.
That is
I by-
gone. Psi, see. Yes. Other students, anybody get this? Or you all have the same doubt?
Got it.
You restate the statement. Let everybody listen.
Sir?
You restate your statement. Let everybody listen.
Sir means actually psi is equal to A into e power minus I by h cross into et minus px, no, sir? But you wrote as AX, means did you, you have shortcutted it or anything?
No. See, when we started our discussion, all the idea we had about waves was y equal to a into e to the power of minus I into omega t minus kx. That is all the idea we had about waves, right? We use
sir.
that concept, integrated the momentum and energy concepts which we took from the quantum mechanical perspective, and we developed a new equation called as Schrodinger's wave equation. Once the Schrodinger wave equation comes, we do not have any relation with the old general wave equation. That is y equal to a e to the power of minus I omega t minus kx. All that matters to us now is the Schrodinger's equation. The Schrodinger's equation is the starting point in the quantum mechanics now. For us, for our discussion, Schrodinger equation is the starting point. Right. Now, in this Schrodinger equation, given any situation, let's say somebody says evaluate the energy of an hydrogen atom. That is a quantum mechanical system. Somebody says evaluate the energies of an electron which is moving at a speed of 10 to the power of 7 in an accelerator. Right. And somebody says evaluate energy of an electron which is trapped in a diode. Right. This is the practical situations given to us. From this practical situations, we take all the information about that particular particle and we put that equation, information and the boundary values in the Schrodinger's equation. When we put all that boundary values in the Schrodinger equation, finally we get an equation like this. This equation is derived from Schrodinger's equation. This equation is for a particular particle. This was solution for the Schrodinger equation. So we got this equation from Schrodinger's wave equation. So this is wave function of the particle. Some of the particle, one particular particle. You understand this?
Sir, means what we substituted in the Schrodinger wave equation, sir?
You will understand in next class. Unless we discuss one practical situation, you will not understand. Right? We'll do that. We'll do that exercise in the next class. Right? You start with the Schrodinger equation. Schrodinger equation is the starting point. You input all the given values in the Schrodinger equation, given information, You will get the solutions. In that solution, you select the proper solution, well-behaved solution, and you arrive at wave function of the particle. This is what you have got. Okay. Next.
Okay, sir.
This is the wave function of the particle, which should have all the information about that particle. Just like the position, momentum, energy, everything. All the information about the particle should be there in this equation. Now, how to get information about position? Let's say, find the location of the position. How will you find? At any given instant of time and space, you will have to find the probability of the particle. Probability of finding the particle. How will you do that? That is called as expectation values. You have to get the expectation value of that particular quantity. How to go about for position alone? So this is the definition of the most probable value of a quantity. It also gives the average quantity over a given range. Okay. Psi has all the information contained in it. We have to extract the desired information. Suppose if you have to get the information about position, this is the expectation value of position. X in the brackets. Expectation value of position. It is integrated. The function is integrated from minus infinity to plus infinity. Here it need not have to be infinity. It can be any given range. Any given range. Okay. X into psi square dx. What is psi square? Psi square is probability density and it is multiplied with x. X is what we need. Okay. This is the expectation value of
Sir,
x.
those 2x are same only, no, sir?
Which 2x?
That is
This-
inside the integration and inside the bracket.
Sir, no, we called it as expectation value of x. This is equal to integration in the given range x into psi square dx. You do this operation, you will get some value. That value is
Sir,
the
Sir, means this
expectation
x
value
is
of x.
different, sir.
Which x? This x you are talking.
The x inside the integration part.
That is x, which here in this psi, no, same x is here.
Means that is just an unknown value, but the outside one is expected value.
Outside is expected value. This x is same as what is inside the wave function. Here we have one x, no? This x and this x are same. If you further continue, what you will get? You will get, I'll just write down. Minus infinity to plus infinity. X into, what is mod psi square? Mod psi square is a square x square dx. Okay. So this you get. A square is constant. Minus infinity to plus infinity. X cube dx. This is what you get for position. This is the expectation value of position. That means you multiply psi square with x and integrate it, you get expectation value of the position. Okay, don't write this. You don't have to write this. Not necessary.
This matter also, sir.
This one you write down, matter, and this one you write down. Okay. Now the question is, for x we know we have to do like this. But if you have to find the energy from this wave equation, what will you do? You cannot just write E over here. If you want to find momentum, what will you do? Can you just write P here and do this operation? It will not work. You understood, no? For position, expectation value of x is equal to integration of psi square multiplied with x. For energy, expectation value of energy, we cannot go with the because integration of psi square with E. E is unknown value. It remains as E only. What will you get finally? E will be there in the final equation. What will you get? You get nothing. If you want momentum, expectation value of momentum is equal to integration P into psi square dx. That also won't work. So there should be some other alternative. For position, this works well, whereas for other quantities, it doesn't work. Equation seems fine, but it doesn't work. For that, the concept of operators came in. See, we have this previously, dou square psi by dou x is equal to I by h cross p psi. Dou square psi by dou x is equal to I by h cross p psi. Okay. Right? Now, you rewrite this. What do you get? P psi is equal to h cross by I dou by dou x. Okay. See, one more thing. Here, when somebody asked why didn't you use d instead of dou? Dou is generally used when you mention that, when you have to mention it is a partial derivative. That means psi doesn't depend explicitly only on x. There may be other variables to indicate that dou is used generally. Okay. Next thing. See, p psi is equal to h cross by I dou by dou x. Now remove this psi. Psi is on both the sides. Compare this psi. Right? You can always compare these two quantities. That means p is equal to h cross by I dou by dou x. Here we call p as p hat. We cannot straight away equate it to p. We'll have to call it as p hat. So p hat is equal to h cross by I dou by dou x. So this term h cross by I dou by dou x is called momentum operator. Is called momentum operator. Now what to do with this momentum operator? Very simple. We have P is equal to integration. Let's fix the range later. Then we have P okay, so expectation value of momentum is equal to integration P into psi square dx. This I'll rewrite as, this psi square is equal to what? Psi square. Can somebody tell me psi square is equal to?
Probability density.
Probability density, and mathematically it is also represented as psi star psi. Okay. So now I'll rewrite this as integration psi star P psi dx. This I'll rewrite as integration psi star h cross by I dou by dou x psi into dx. Where is P now? P is now equation. We love P, but instead of P, we are using the operator. We are using the operator which equivalents P. So this P is now operating on our side. This P is now operating on our side. See here, dou by dou x of psi. Dou by dou x of psi. So this P is operating on psi. And we get the expectation value of P. Similarly for the momentum. So this also, in the light of that, this also can be rewritten as x of, sorry, the expectation value of x is equal to integration psi star x psi into dx. This is how it is. So here x itself is the operator. When it comes to momentum, this is the operator. When it comes to energy, this is the equation we had previously. You rewrite this, and this is the energy operator. E is equal to IH cross dou by dou T. This is the energy operator. Write down this.
Sir, how did you wrote psi square into psi star, sir?
See, psi square can also be written as psi star psi instead of that mod. If at all you take out that mod. See, this was taken straight away from the, what is it? Just a minute. So this was taken from the what is this? Minus infinity to plus infinity psi square dx. It was taken from the definition of probability density. Okay. And this x was included to take the average value or value at that particular position. From this, we rewrote this. This can also be rewritten as, if that is except that mod, this can also be written as psi star psi x dx, or x into psi star psi dx. Okay, it is general, it won't affect much. See here, one thing you should remember, mathematics is used by the physicist to understand the physical concepts, right? We do not go very, what is that, strict with its mathematical rules. Mathematics is there, but it is for our use, right? What is the rules, exact rules, what you learn in mathematics, the exact rules we don't have to apply, because physics is all approximation. Whenever there is a situation, whenever given situation, if it works, yes, we use that way. There is nothing wrong in that. You don't have to be very strict in using mathematics in physics. Mathematics is very essential. Without that, we cannot proceed. That is true. But use it at our advantage, right?
Okay, sir. Sir, also you have to write all these, sir.
This you should know. You should know. So this is the operator for energy. This is the operator for energy. So whenever you have to find energy from a given wave function, right? You'll have to write an equation like this with energy here, and then you'll have to write like this with this one. Okay.
Sir,
Yes. We'll solve one or two problems, then you will understand.
Sir, which one we have to note down, sir?
You have to note down this one. This one you note down. Okay. Afterwards, you note down the operators, these two, and I'll give you the list of operators. Note down this list. Yes, you are saying something.
Sir, this one, sir, above one. Expected value of momentum also, no, sir.
Expectation value of x you write down. Afterwards, you go to operators. Okay. To find the expectation value of momentum and energy, we need the use of operators.
Means you wrote already here, sir. Expectation value of momentum.
I didn't get.
You have already wrote the expectation value of momentum, no, sir, here.
This one.
So we have to note down this is now only
No. Just write down to evaluate the expectation value of energy and momentum. We need operators.
Sir, are these operators, how are they derived, sir?
I told no. Here, the derivation is here. This is derivation
but
for
how the sign is
Dou psi by dou x is equals to I. That formula is no, sir. First equation.
This we got from the got we when we are evaluating the Schrodinger's equation? Did you forget last class? You check
Yes,
it.
sir. But that is general wave equation, no, sir. If equation changes, that
But it
will
is,
also change.
yes. But when it momentum comes, see, that is general wave equation. We have converted general wave equation to Schrodinger equation. In that step itself, we have got this also, right? We have got this, and here we are equating P to H cross by I dou by dou X. So wherever we have to extract the information about P, we cannot keep P as it is. Therefore, we will have to replace it with a mathematical operation. That mathematical operation is H cross I by dou X.
Okay, sir.
Sir, can you
You are
once
not
again tell why operators are used?
See, you have to get the expectation value, or you have to get the information about the position, momentum, energy, right? Do you agree?
Yes, sir.
Right. Fine. To get the information about position, there was a very simple method where you have to, this is the probability density. Multiply that with the position before integration. That gives the probability density, that gives the position of that particular particle, right? In that given range, of course. That was a very simple thing. But okay, it is very easy to, what we have to do, we have to just do multiply x with psi square and integrate it. That's it, very simple. But how to get the momentum values or the energy values, that was difficult. See, guys, it is 9:24. I will leave now. Okay, let's take it on.
Now after writing, sir, now after writing operators, we have to write this one also, sir. Expected rate of P you wrote above.
Now you do one thing. Don't write anything. Okay, Monday we'll discuss.
Okay, sir. Okay, sir.
Okay.
Thanks.
Monday we'll discuss. Yes, go on.
Okay, sir. Thank you.
Sir, how is P cap different from
Your voice is breaking. You're not clear.
Sir, am I audible now, sir?
Now it's fine.
Sir, how is P cap different from T, sir?
See, P cap, when we say P cap, we call it as operator. We call it as operator, mathematical operation. That's why we say it is P cap. It is operation. We'll replace P with operator. Okay.
Yes, sir. Okay, sir. Thank you, sir.
Sir, please stop recording.
Yeah, I'll do it. Thank you, guys. Take care. We'll meet on Monday. We'll go.
Thank you, sir.
Thank you, sir.